I'm mostly going to talk about the research we have done in a project called Reliable and Real-Time Wireless Automation in this UBCOM program. I'm from Aalto University. We have a wireless sensor systems group, which is a kind of cross-departmental research group there, which focus on all kind of things, wireless things and applications for that. These modular hardware and software solutions is kind of the main results from this our project. So this will be something that in the end of this year we will publish, hopefully what we have developed in this project. So one slide generally about the project. The main goal for us and for the industry partners is to develop wireless platform for industrial use. So industry have many use cases where by just adding more sensors, preferably wireless because they are easy to add on existing systems, they can get a lot of added value by processing and analyzing that. So I will give some examples later on. But what is needed is flexible hardware. So we have different requirements for different industry processes and factories. And also the development should be as simple as possible. So we would like to have some kind of hardware independent development of the applications. And in industry, reliability is very much needed because we have factory or some process that runs in real time. We need data from that in real time also. So what we have studied in this project is kind of this wireless embedded services. We have wireless sensors, do some embedded processing, and that wireless sensor system is giving some useful information for the process or for the factory. We have 5 industry pilots. Roughly the topic of those pilots are wireless monitoring and wireless diagnostics of different processes, wireless control, and also wireless in working machines. So the outcome of this is these flexible new hardware platforms, which are released as open source platform, open source tools. And the project is joint with Aalto University, University of Vaasa, and VTT Oulu. There's the web page, and Riku Jäntti is the head of the project. So some words of what we are talking about now. So you know wireless sensor network. It's basically you have sensors collecting some data. You have a gateway where you collect all that data, and then you have some server where you process that data to get some added value of the raw data. Well, wireless sensor network have the drawback that what is the added value? You measure something and then you collect it, but how can you improve or get some added value? And as has been said already many times, that's the silo effect. You have this one system for one thing. And Internet of Things is kind of reaction for that. You have lots of devices, and by interconnecting those devices, combining the information from all these, you can construct some service that is really useful for the user. So the user can either be in this cloud of devices connected, or then there could be some server collecting useful information and making processing and presenting that to the user in some web application or so on. Well, wireless sensor systems, which is the research focus in this project, is slightly different. There you have kind of a wireless sensor network, but you do the processing that you would do, or combining of information that you would do in Internet of Things, you do it in the network. And this has several reasons. One is that the processing of data needs to be very, very fast and efficient. The wireless devices have batteries. We cannot transmit the raw data as you probably do in wireless sensor networks and also Internet of Things. You really have to reduce the data by processing it in the network before you transmit it to the user. And also the speed which you have in factory or process automation, it can be like you have deadlines of 1 second and accuracy of the data should be in millisecond range. So that is very difficult to accomplish with Internet technology, like in Internet of Things. In the end, the useful information is collected at the gateway and either sent to a user or then to an automation system or some other. So it could be like a machine-to-machine type of applications that the wireless sensor system is delivering some information there. So this is a summary of the previous picture. So wireless sensor network, the research side, you think about networking issues, data processing issues, and so on. My colleague says that these are kind of measure, transmit, and amen type of applications. Quite simple. You actually don't need much more than networking. Internet of Things is internet technology and about connectivity and interoperability of devices. So in this case, it's devices and you interconnect them and you get hallelujah. Wireless sensor systems, I would describe them more as wireless sensor network and also the application running the intelligent stuff running in the network. So there you have sensing, you process data, but you also have cooperation inside the network among the devices. So it's measure, process, and heureka. Okay, so what are these kind of more advanced applications that you cannot make with in many cases in industrial applications that you cannot make with Internet of Things technology? So those are in kind of industry machine-to-machine applications. You can be like production, quality or management, or cost or energy efficiency applications. In wireless automation, you have this kind of real-time control, data fusion, model identification, where it's not in control. You have to work in real time, so passing the data through some cloud service or anything like that is not feasible. Data fusion is of course very natural to do as close to the raw data as possible to reduce the amount of data that you transmit, to save the battery, and also this kind of model identification. Get raw data in and you can do the identification inside the network and you have a model as the end result, which is easy to transmit wirelessly. You can have all kinds of intelligent network doing data fusion, distributed processing, distributed condition monitoring, and so on, which are topics that are studied in research centers or universities. And also networks with heterogeneous measurements, data fusion, compression, and aggregation is clever to do in the network than transmitting the raw data somewhere to do the processing. But in these applications, processing in the embedded devices require quite complex hardware, and also the software development is much larger. So here's an example. We could have some case like this, that you have a bunch of different sensors you might have a coordinator inside the network, wireless network. You have some simple wireless sensors, you have some aggregator, you have some more devices with more computation capability and so on. Then you have some system manager and gateway to the internet, to a remote manager user, or then the plant networks or the rest of the automation system. And so there are different roles, many different roles in this wireless network. But the question is that can we somehow have some similar or same hardware for all these use cases and roles? So different use cases, I mean different implementations in different factories and so on, which might have different requirements also. So this was our target for the project, to make this kind of hardware that you can use in different cases. So when you think about what kind of hardware you need, you ask, do I have enough resources? But actually you should ask, what resources do I need? So when we develop this for different applications, you might need hardware redesign for a specific purpose. And if you design for some special purpose, it becomes non-reusable. And development time is then longer if you make it for a certain product, certain purpose, but cheaper end product might be possible. So if you develop the software or develop the whole system, you need to develop hardware, might have multiple processor and other modules in your hardware, and then you have to do debugging and the embedded software development. And software development should also start as soon as possible, and hopefully even before you have the final hardware. In software development, you first do the design, then you do the development simulation to test that it works, and then the deployment. So these are the things that I will talk about in the presentation. So we start with modular hardware design. Yeah. So these are the technical parts, which I'm not going to go that deep. I just give brief description of these. So for different things, we could have different processors. So we have, for wireless communication, we have communication processor, and then for doing the data processing, we have a main processor. And then there could be also sensor actuator management and so on. And then then there are issues like time management, power management of these, when you have multiples of different processor and also devices or peripherals for the system. So how can we make this hardware so that you can modify it for different purposes? So we could pick and place different hardware components and software components. So I skip to this. So this is our what we have developed for wireless node, where you have a basic mode which has a main module and power module, and it works with those components only. Then you can have a wireless processor and power source attached to that, and then you can have even to the basic node more power sources and wireless processors. But for modifying this for different purposes, we have developed slave modules, which can either be active, which has a processor of its own, and the interfaces for sensors and actuators, or then an extension slave module, which can have extensions to different resources and peripherals. And then as a special case, we have this passive slave module, which is an interface for sensors and actuators. So this is called a p-root node. And here's some technical information about that. I'm not going to go through this. And then example of power management. Now when we have these different slave modules which you can attach to the node in depending on the requirements that you have for the application, what you need to do, then the power management of these different sub-components becomes difficult. So we have studied this also. And here are pictures from the latest revisions. At the bottom you can see the main module, and then attached to that we have different of these sensor extensions. And just as ongoing work is this low power node, which we study also have this energy harvesting module that's made with similar design as this p-root node. But this is ongoing. So I go to the development of the wireless sensor systems and the software development. So for applications we have different constraints, and then we need to optimize the software components. And in this case we are working at close to hardware level, so we cannot separate low-level components or hardware to the software. So we need some kind of. So basically, I skipped to this. So in the design, we first have to design the system where simulations is a very good tool to determine design criteria and so on, and the optimal operation point, and evaluate the performance that we can expect. Then we do hardware and software development, and then network level development or integration, and then we validate. So there are many stages, but how going from one stage to another? Can we do this very efficiently? And this is our development environment. So basically we have a simulator manager which can manage multiple node simulators, and these node simulators can be debugged, and so when we develop the code we can immediately simulate the thing, and exactly the same code we can port to the hardware. So there are lots of details about the network and node simulators. I'm skipping that and show some screenshots of the tool where you can see consoles and graphs plot from different parameters what we want to measure from the simulator to evaluate the whole system. So these are the hardware design and the software design, and these simulation tools are the outcomes from the project, which we are still working on those, and that's all. Thank you.